Buenas tardes, bienvenidas y bienvenidos a este coloquio del Instituto de Investigaciones en Matemáticas Aplicadas y en Sistemas. Este es el primer coloquio con el que iniciamos una serie de coloquios que forma parte de nuestros festejos por el 50º aniversario del Instituto. Ahora voy a cambiar a inglés. It's a pleasure and an honor to present Professor Robert Calderbank as a speaker in today's colloquium. I think that his career is an example of how successful interdisciplinary research and teaching can be, which I hope we can take as inspiration here at our institute. Particularly, Professor Calderbank's career synthesizes a very productive interaction between abstract mathematics and concrete engineering applications, a career which has advanced theoretical understanding and practical implementation across communication, information theory, and quantum computing, as well as implemented initiatives for students to learn across disciplinary boundaries. Professor Calderbank earned his Bachelor in Science from Warwick University in 1975, his Master in Science from Oxford in 1976, and his PhD from Caltech in 1980, all in mathematics. Professor Calderbank joined the Mathematical Sciences Research Center at Bell Labs in 1980, when he first started applying algebraic structures to solve engineering problems. During his time at Bell Labs, Professor Calderbank helped to develop the voiceband modem technology, which was widely licensed and incorporated in over 1 billion devices, which some of you might recall by the burps and squeaks they made when connecting to the internet. This work demonstrated how algebraic coding theory, that is the mathematics of error correction, could be translated into commercial products that enable internet connectivity. His contributions to coding and information theory won the Institute of Electrical and Electronic Engineers Information Theory Society Paper Award in 1995 and 1999, recognizing both the mathematical elegance and practical impact of his research. In the 90s, Professor Calderbank joined AT&T Labs, where he co-invented space-time codes, applying group theory and coding theory to the engineering challenge of wireless transmission across multiple antennas. This space-time coding technology has been incorporated in a broad range of 3G, 4G, and 5G wireless standards, illustrating how mathematical abstractions can reshape entire industries. As Vice President of Research and Internet and Network Systems at AT&T, he managed both fundamental research and its commercial translation, overseeing intellectual property and licensing revenue. Together with Peter Shore and other colleagues at AT&T Labs, Professor Calderbank developed the group theoretical framework for quantum error correction, which influenced the way physicists view quantum entanglement and provided the foundation for fault-tolerant quantum computation. This work on CSS, or Calderbank-Shorstein codes, is another example of mathematical rigor applied to emerging engineering domains, creating theoretical frameworks that would guide decades of subsequent research in quantum computing. After leaving AT&T, Professor Calderbank became a professor of electrical engineering, mathematics, and applied and computational mathematics at Princeton University, where he directed a program in applied and computational mathematics. This interdisciplinary appointment reflected his capacity to work across traditional academic boundaries. At Princeton, he developed courses connecting theoretical concepts to practical bandwidth engineering, training students to think simultaneously as mathematicians and engineers. Finally, Professor Calderbank moved to Duke University, where he served as Dean of Natural Sciences from 2010 to 2013. And he currently holds professorships in computer science, electrical engineering, and mathematics, directing Duke's Information Initiative. This position synthesizes his career-long integration of mathematical theory and engineering practice, treating information as a unifying concept that connects disciplines. His current research spans quantum error connection, wireless communication, and data storage, consistently demonstrating how sophisticated mathematics enables practical systems. I invite you to check the website for the Roads in Information Initiative, which describes the diversity of projects that students in data science are working on, spanning areas as diverse as computational humanities and art restoration. Professor Calderbank was elected to the US National Academy of Engineering in 2005 for leadership in communications research. He received the 2013 Institute of Electrical and Electronic Engineering's Hamming Medal for contributions to coding theory and communications, and the 2015 Shannon Award, the highest honor in electrical engineering and computer science. In 2022, he was elected as member of the American Academy of Arts and Sciences. Throughout his career, Professor Calderbank has maintained that the most powerful engineering innovations emerge from deep mathematical understanding, while the most interesting mathematics often arises from confronting real engineering constraints. His work demonstrates that his dialogue produces results that neither discipline could achieve alone. During this visit to our institute, he has been generously sharing his insights and advice on how to promote interdisciplinary research and teaching here at our institute. We are honored to have him as a speaker today. So please join me in welcoming Professor Calderbank.
Okay. Thank you. Well, I've been introduced many times, but I don't think that I've ever been introduced quite so fully. And it's going to be very hard to live up to that. So what I'm going to try and do today is to tell you about how a particular algebraic construct, the Heisenberg-Weil group, provides a common foundation for quantum computing and wireless communication. Now, Duke University requires me to put disclaimers on the cover slide. And the disclaimers are that in the quantum space, I'm an advisor to IonQ, which is a publicly traded quantum computing company in the US. And I'm also chair the technical advisory board for Cohere Technologies, which is a wireless company. What the disclosures mean is that I have a conflict of interest, and you should take whatever I say with a grain of salt. All right. So I'm going to start with quantum. And what I'm going to try and do in the next 15 minutes or so is to give you a feel for how Peter Shore and I came to CSS codes. And so here, a little bit of history. So in 1995, Peter publishes this algorithm for factoring integers that's basically quadratic, whereas the best that we know is essentially exponential. And physicists looked at this and they said, yeah, well, but you can't do this because you can't build a quantum computer, because to build a quantum computer, you need to do quantum error correction. And in quantum theory, you have this no-cloning theorem, and famous physicists like Charlie Bennett thought that meant you couldn't do error correction. Then Peter proved them wrong by producing a 9-qubit code. And in the talk today, I'll talk about half of that code to give you an idea of how it works. And then we went on to develop CSS codes and stabilizer codes to show that it was just as easy to make quantum codes as it was to make classical codes. And today, there's all sorts of research going on in things called LDPC codes or hypergraph product codes. And I think that the interesting area in quantum is, I think that making a quantum computer is hard. And in order to make one, the people that know the physics have to work together with the people that know mathematics. Because it's only by putting together things that are easy for one of them that you'll actually manage to make one. So I'm going to introduce quantum codes through classical codes. So I'm going to tell you a little bit about classical codes. I'm going to begin here with a short history of coding theory. And here, so in 1948, Shannon introduces this notion of capacity. So he has channels, and there's a theoretical bound on how much information you can transmit over a channel. That's the channel capacity. He didn't actually tell people how to do that. What he did was he showed by averaging over a random ensemble that there was some code that worked. And he left it to subsequent generations to find that code. Now, one of the things that actually students forget these days is that in the 1950s, 1960s, 1970s, and early 1980s, there were really no such thing as computers. In the early 1990s, if you wanted to do dynamic programming on your laptop, you could do it on maybe an 8-state graph. Today, your cell phone does dynamic programming on graphs with 10,000 nodes. And so in the 1950s and 1960s, coding theory was mathematics. It was all sphere packing. And, the fundamental mathematical questions, which have fascinated number theorists for ages, like how many spheres can touch a given sphere in n-dimensional space, that's what coding theorists thought about. And it's not like it was completely useless, because things like Hamming codes and Reed-Solomon codes, they came out of that way of thinking. And your computer, I'm sure, has a Reed-Solomon code in its data storage unit. And so the codes that were produced in this era, they're in tens of billions of devices. Perhaps the high point in recent years is this demonstration by Marina Vysotská that in 8 dimensions, 240 spheres can touch a given sphere, and that's best possible. And these spheres are associated with the E8 lattice. This kissing number problem is remarkable because we know the answer in dimensions 2, 3, 4, 8, and 24, and that's it. Anyway, all right. Now, what happens when computers start to show up is that the nature of coding theory changes. It becomes about algorithms and convergence. LDPC codes, which I'm not going to talk about, are defined by graphs, and decoding works by passing messages from node to node. And whether it works or not has to do with, does your algorithm converge? And so the nature of coding theory has changed. And that's true in the quantum world too. But let me go back to the beginning. I'm going to go back to Hamming codes. I'm going to do Hamming codes because when Peter and I were thinking about CSS codes, we were actually thinking about how to make the Hamming code work. So I have to tell you, so in classical binary coding theory, there's an error model, which is bits get flipped from 0 to 1 or 1 to 0. And so there's a model, it's called the binary symmetric channel. And that little graph says that if you put in a 0, it stays a 0 with probability 1 minus p, and it gets flipped with probability p. Same thing for 1. And so you put in a 0, and statistically, this is what you expect to observe. And actually there's a difference in coding theory between electrical engineering and computer science. In electrical engineering, communication is statistical. In computer science, computer scientists are paranoid. They prove theorems about worst case errors. So they imagine an adversary that knows what they want to do and is intent on frustrating them. But communication theorists are different. One of the questions you can ask yourself is, if you had one of these binary symmetric channels and the crossover probability was a half, could you send any information at all? The answer is no. Anyway, well, what is coding? Well, if you think about what's the probability of transmitting 4 bits error-free? Well, it's 1 minus p to the 4th, because these are independent events. A Hamming code uses 7 channel uses to communicate 4 bits. So instead of sending 4 separate bits, we're going to entangle those 4 bits into a vector of 7 bits. Now we're going to have 16, that's 2 to the 4th of these vectors of length 7, and we're going to select them so that they are orthogonal mod 2 to all the rows of this matrix H. This matrix H is called a parity check matrix. Now the code, it's a linear space in GF2 to the 7th. And so 7-dimensional binary space is a union of 8 cosets of that space. What Hamming did was he described how to use the parity check matrix to correct errors. What he does is you send a code word C, and let's say one of the bits gets flipped. He calculates this syndrome, H, C plus E transposed. What that does is it identifies a coset. And now I said communication is statistical. So what that means is that there is a most probable way of getting from the code to that coset, namely flipping a single bit. You know, how probable are errors? Well, it's the number of errors you flip, number of bits you flip. So the most probable error is the one that flips the fewest bits. So the idea here is you calculate a syndrome, the syndrome identifies the coset, you correct using the most probable error to have happened. It's not the error, it might not be the error that actually happened, but statistically you're on the right track. Okay. Now then, I'm going to abstract this. I'm going to say, because I'm going to reproduce this for the quantum world, and then I'm going to explain the quantum world. So here you've got an error group. So these are just flipping bits. Adding a binary vector is flipping bits. And you have a stabilizer code, a stabilizer group. These are just the bit flips that preserve the Hamming code. So these are the bit flips that live in the code itself. And here I've made this distinction between things acting as a group and vectors in the code. And it's a bit artificial in the binary world, but it will be less artificial in the quantum world. There's something, these cosets, we take the code C, and the whole space is a union of cosets. You start off in a code, the error moves you to a coset, you identify the coset, you move back using the most probable error. Okay? That's that is classical binary coding. Now then, in the quantum world, I'm going to tell you about qubits. I'm going to concentrate on 3 qubits, and that's going to be an 8-dimensional Hilbert space. The error model, these are going to be bit flips and phase flips, and the error group is going to be something called the Pauli group. And how am I going to make codes? I'm going to define a commutative subgroup of the Pauli group, and the fixed space of that group is going to be the code. Errors are going to take me from that code to some other part of the resolution of the identity. I'm going to identify which part, and then I'm going to go backwards using the most probable error. So that's how it's, so now I'm going to explain how that works for 3 qubits. Now, one thing I forgot to say here is that this paradigm for coding, it actually doesn't care about which code word you send. And that is actually important in the quantum world, because I'm going to be doing a quantum calculation, errors are going to happen, I'm going to correct them. I can't be finding out anything about the vector in the space where I'm doing the calculation, because otherwise that destroys the calculation. And so that's going to be important. All right, quantum bits. So here's a little bit of mathematics. So classical bits take the value 0 or 1. Quantum bits take superposition of 2 base states. And it's 2 dimensions, so the base states are 1, 0, and 0, 1. They define a 2-dimensional Hilbert space. What about more quantum bits? Well, we make more quantum bits by taking tensor products or Kronecker products. And Kronecker products are matrices the way students think they ought to work. That is to say, how do you, so here we are going from right to left, and so this is the, so we've got 2 quantum bits, and the second bit is in state 1 and the first in state 0. And here 0, 1, 2, so that's the state of the system. And how do I get 0, 1, 0, 0? Well, I take the Kronecker product of these 2 things. This was This was E0, that was E1. And so you can see how these are put together. Right, so I've got my 2 to the m dimensional Hilbert space, and I've identified all of the vectors. And in quantum, there's something called a resolution of the identity, and that's defined by operators that project onto spaces, and they have the property that they sum to the identity and they're pairwise orthogonal. In quantum mechanics, which I'm definitely not going to explain in this lecture, you measure with respect to a resolution of the identity. What happens as a result of the measurement is you project into one of the subspaces and you learn which subspace. In the beginning, you are in each of the subspaces to some degree. Measurement projects you into one of them. So, now then, what are errors? So there are flip errors. So you look at that X and think of the 2 rows and columns as being indexed by the 2 states. Here we're flipping the 2 states. That's a phase error, and this is a flip phase error. In quantum mechanics, all of the operators have to be Hermitian. That's where the I comes in. And, well, what about multiple qubits? How do we get multiple errors? Well, we do this Kronecker product trick again. So we're interested in combinations of flips and phase errors, and the things in the Pauli group are given by this kind of Kronecker product. Now, perhaps the simplest ones are the ones that just involve the phase errors. They're diagonal. And when you take a Kronecker product of the diagonal things, it stays diagonal. So here we are. Here are 2 diagonal transformations. This is what's happening in the bit flips. This is what's happening in the phase flips. And there we are. You can figure out the entry. And now, my stabilizer group is this commutative subgroup. It's generated by those 2 matrices. The group projects onto the fixed space. You can see these are 2 projection operators. You have to pass both projection operators in order to get into the space. When you apply an error, what happens is you conjugate these projection operators. And you change these signs. There are 4 different ways to choose the signs, and so that's how we get these plus, 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 minus, minus, plus, minus, minus. And every error, every flip error, every phase error permutes these guys. So you're doing a calculation, you start off in V++, and something nasty happens, an error happens. It goes somewhere. You have to find out where it goes without finding out any information about what the vector was. And that's that syndrome decoding idea. And this bit flip code, which is half of Peter's 9-qubit code, is you start with V++, so you're starting in here, and then some error happens, and this code is able to resolve or correct every single bit flip error, because this is what happens to a bit flip in the 2nd qubit. It takes you from here to here. In the 1st qubit, it takes you from here to here. And the 3rd one, it takes you from here to here. So you have 4 of these spaces. You try and figure out which one are you in. How do you figure out which one you're in? Well, you apply the two generators in the stabilizer group. Do they come out positive or do they come out negative? If it comes out positive, positive, you stay in here. If it comes out negative, positive, you ended up in here. And then what you do is you correct using this guy, because it's the most probable error. And so this is the, in general, we came up, Peter and others, we came up with this idea of stabilizer codes where they're defined by commutative subgroups of the Pauli group. They determine resolutions of the identity. And properties of the group give you the error-correcting properties of the code. I have to say that we submitted this paper to PhysRev Letters, which is really the top of the physics tree. And we were assigned a shepherd because this paper, I mean, the interesting thing about PhysRev Letters papers is that they're 4 pages. And page 1 is something like, the most important problem in the world is X. The most important discipline in the world is physics. Within physics, the most important area is this one. We do this. And our paper wasn't quite like that, and it had an awful lot of mathematics, and it was considered risky. And so we got a shepherd who was supposed to translate between us mathematicians, computer scientists, and the regular physicists. CSS codes are special types of stabilizer codes. The stabilizer group is a direct product of bit flips and phase flips. And the last thing that I want to say is there's this group, and it's called the Pauli group in quantum mechanics. It's actually a manifestation, characteristic 2 of the Heisenberg-Weil group. And it's a group, actually the way to understand it is it's a group that's really trying to be commutative, but it's not quite making it. So xy is equal to yx or minus yx, and the which one depends on this symplectic form. What plays an important role in quantum information science is something called the Clifford group, which is the normalizer of the Pauli group in the full unitary group. And transformations in the Clifford group correspond to different ways of representing quantum bits, or they correspond to how do you implement quantum gates on a quantum error-correcting code. All right, that's quantum. And this Pauli group is the Heisenberg-Weil group. Now then, let me tell you a little bit about wireless. So this is a great quote by George Orwell. Every generation imagines itself to be more intelligent than the one that went before it and wiser than the one that comes after it. It's a great quote. What's shown on the screen, in wireless there are generations of technology. We're currently on the 6th generation of technology. They progress every 10 years. Every time Ericsson needs some more money, they have a new generation. And here, what I've done is I've tried to give you some indication of what the prevailing application was. Here it was just voice. Here it was the beginnings of data. Here it was wireless connection to the internet. And in the 6G, it's expected to be the integration of sensing and communication and the introduction of artificial intelligence. So here I want to talk about sensing. And this is a picture of Philip Woodward, who was a very distinguished radar engineer in the UK. He's also a virtuoso clockmaker. And in 1953, which is only like 5 years after Shannon, he published this monograph on probability and information theory with applications to radar. And in that paper, he proposed that you think of radar as a game of 20 questions with an unknown operator. So the unknown operator is the scattering environment. A question is a waveform that you probe the scattering environment with. An answer is a return. You're trying to discover the scattering environment. You're trying for a sequence of questions that reveal the operator. And what makes a good question? And I'm going to talk about this waveform, which is mathematically a pulse in the delay Doppler domain. This is its time domain representation. It's a pulse train modulated by a tone. And here, this is a picture of wireless, right? So you're here, you send out a signal X into the world, it bounces off stuff. If the stuff it bounces off is stationary, you just introduce a delay. If the stuff it bounces off is moving, you get a shift in frequency, a Doppler shift. And so, in a sense, you send out a signal here, and what you receive is shifts in delays and Doppler of that signal, superimposed, of course. Here, the height is how much you get attenuated by the reflection. And this group of delay and Doppler shifts, that's the Heisenberg-Weil group, in odd characteristic this time. And what we're going to be thinking about is how to design an X. What kind of X would you like? You'd like to design a function X which is moved about by these elements of the Heisenberg-Weil group. So that's what we're going to go. And this is a slide that I use for electrical engineers because I use it to say, this isn't very complicated. You teach this stuff. You teach linear time invariant channels, which are channels where there is no Doppler shift, where you send a pulse in the time domain, you wait for a bit, you discover the channel, you equalize. So a time domain pulse is a good question when you don't have any Doppler shifts. Now, suppose you do have Doppler shifts. So this is LTI channels. Now you do have Doppler shifts. In the LTI channel, your output signal is some kind of convolution with the input signal. In this kind of channel, it's still a convolution, but it's got a twist. It's got phases in it. We call it twisted convolution. But it's still the case that you send a pulse, and you get a bunch of replicas. What we say to wireless engineers is we are going to define a way of signaling. It's going to be defined by a delay period tau p and a Doppler period nu p. How should you choose these numbers? We say, you're a wireless engineer. Cells are only so big. You're only going to encounter delays in this range. I want your delay spread to be less than your delay period. Same thing with Doppler. Stuff only moves so fast. There is an upper bound on the Doppler spread you will encounter. The Doppler spread should be less than the Doppler period. And what will happen is that provided these conditions are met, this way of communicating is very predictable. Here, we're going to be thinking about, so what I want to try and understand is, and so this is going to be a very simple group theory thing in the end, but what kind of signals are moved about by this group? So we're going to have a basis of carrier waveforms. How many things in the basis? BT, where B is the bandwidth, T is the time duration. That's the time bandwidth product. And this is how the outputs Y are related to the inputs. W is Gaussian noise. And we have this Heisenberg-Weil operators that move the signal around. They form this Heisenberg-Weil group. In the quantum world, the scalars were just plus or minus 1. Here they're a little bit more complicated. But the structure is still the same. It's a non-commutative group, but if you mod out by the scalars, it's commutative. And how do you identify these modes that are moved about by the channel? Well, it's kind of easy because you have these BT carrier waveforms that are getting moved around. And you have this group that has order BT squared. And now you ask yourself a simple group theory question: what's the stabilizer of a carrier waveform? Well, it's a subgroup of order BT. How is it acting on a waveform? It's acting by complex multiplication. Complex multiplication, multiplication by a phase, is commutative. Therefore, you've just identified a maximal commutative subgroup of the Heisenberg-Weil group. And that's what a carrier waveform is. All right. And you can keep track in Doppler and delay of the things that act by the complex phase. This is a maximal commutative subgroup. This is the one that's associated with this waveform. Now I want to talk just a little bit about these symplectic transforms. Here, so I have these carrier waveforms which were like this guy. And now I'm going to think about how do I move them around? Well, there are these operators which are called discrete affine Fourier transforms. The important thing about them is that they have something quadratic up there. And basically the message here is quadratic, shift, inverse quadratic gives you a linear transformation. Let me just explain. If you're in the military and you're firing missiles, the missiles have to maintain a constant height above the ground. How do they do that? They chirp down, so that's a quadratic function. They collect the return, and then it's like they have a quadratic function f, and they do f of x plus t minus f of t. And that's a linear function. They solve a frequency problem, and they correct their height above the ground. If you're on a ship, you spend a lot of time listening for very faint chirps, because there might be very bad things that are coming towards you. So, anyway, so these are symplectic transforms. And these are transforms that normalize my Heisenberg-Weil group. What is it that they do? Well, they do some good things from a practical point of view. If you're a radar engineer, this is a really ugly waveform because it's peaky. You don't like peaky waveforms, you like noise-like waveforms. And what this transform does is it makes you a noisy waveform. The other interesting thing that it does is that it rotates that subgroup. So when you have a normalizer of the Heisenberg-Weil group, and you act on the Heisenberg-Weil group, it takes commutative subgroups to commutative subgroups. And so it'll take that commutative subgroup to another one, a rotation of it. That's the linear transformation. And if you're in, so this is discrete stuff, but if you're in the continuous radar world, you're interested in waveform libraries, and you make them in this way. Let me say just a little bit about ambiguity. So perhaps I should, should say this. So you send a waveform that illuminates a scene. You take the return and you correlate it with the original signal. So that is, you say you take an inner product with shifts in delay and Doppler of the original signal. That set of inner products is called an ambiguity function. And it basically imposes a blur on the scattering environment you're trying to understand. The ambiguity function, there's a certain volume under the ambiguity surface that you can't avoid. It's basically the square of the energy of the waveform. What radar engineers do is they move the surface around so that they can see more stuff. So that's basically what radar engineers do. And what Woodward did in 1953 was he proposed using a waveform which was narrow Gaussians modulated by a wide Gaussian. When he calculates the ambiguity function of a narrow Gaussian, he gets this. So practically, what's an ambiguity function? I'm looking for something. This red ellipse says what I'm looking for is somewhere in that ellipse. I don't know where. It's all equally probable. So that's a problem with a narrow Gaussian. It's a problem with a line, it's a problem with a chirp. And by breaking it up in this way, he produced an ambiguity function which was a lattice. So it's much easier to find targets, much easier to find multiple targets. And that structure that he proposed in 1953 looks a lot like the waveform that I was talking about. So that's the waveform that we were talking about. And then I'll just close with a few words about delay Doppler, because there's a fundamental correspondence between the time domain and the delay Doppler domain. So the time domain is about quasi-periodic sequences of length mn. The delay Doppler domain is about m by n quasi-periodic arrays. See, because when I say a pulse in the delay Doppler domain, if you're a physicist, you say, you can't have a pulse, because that would be improperly localized in delay and Doppler. It would violate the Heisenberg uncertainty principle. And so what do mathematicians do? Mathematicians cheat. They define a quasi-periodic function. So when you move in delay, you adjust by a phase. You move in Doppler, you don't do anything. But here I've defined a mathematical function on the entire domain. So I'm legal. Yet, for the things that I'm interested in, they all take place in this square. So it's like I'm as good as localized as I might be. So that's that. And this is the correspondence between what happens in the delayed Doppler domain and what happens in the time domain. Here, you take this resolution and you break it up into m things in delay and n things in Doppler, so you have mn carrier waveforms. Mn is bt, and so this is how you make the waveforms. How do they look like in the time domain? They have this pulse train that's where the pulses are separated by tau p. There's an offset, which is given by this number, and the frequency modulating the function is given by the offset in the other direction. And this transform, zt, is something called the Zach transform. Here's just a picture about all the stuff that goes on in the background. Actually, this picture is perhaps even more intimidating. So this is a picture of a transceiver. It's what happens at the transmitter, what happens at the receiver. So go back to here. What happens is you make signals up here in the discrete delayed Doppler domain. You move it into the continuous domain. At this point, they're just delta functions, so they've got infinite time and bandwidth. That's not very useful. You put on a transmit filter that gives them finite duration, finite bandwidth. Then you move them to the time domain. You transmit them in the time domain, and then you match filter on receive and go back. So that's how it works. And what's special about these geometric modes is the relationship between the input and the output. Just like an LTI channel, it's given by convolution. So you can send a pilot here, and you can just read off your channel. And so that's that. And machine learning, well, you can just, there are situations where you don't actually have enough time and bandwidth to resolve the channel. And we don't care. We don't actually care about what channel. We just care about the input-output relation, and we can read that off. So we read it off. And here is a picture where we're not able to estimate the channel. If we could, this is the performance that we would get. This is the performance we get just by reading off our model. And so here, what I would say is we have, in all the generations before, done communication based on mathematical models, where those mathematical models have parameters, and we try and estimate the parameters. And we, I think, are moving into an era where that will not be true to the same degree. We'll still try and take advantage of physical intuition, but we will try to introduce techniques from machine learning. All right, I think this is the conclusion, which is that in the end, it's all group theory. So in the later part of the 19th century, Felix Klein had this Erlangen program where he said, well, you should really understand things by understanding the groups that preserve them. Okay? It was a very influential program. And in a sense, that's what we're doing here. There's a group, the Heisenberg-Weil group. It has a manifestation in the quantum world as the Pauli group. Has a manifestation in the wireless world. And we're taking advantage of that group theory to signal on the channel. So it's kind of a principle with coding theory is that you have a group of errors, and you use that group of errors to develop coding schemes. So all of the coding schemes come out of that group. All right. Thank you all for coming. Happy to.
Time for questions. Si alguien quiere hacer una pregunta en español y la traducimos, no hay ningún problema.
Thank you very much for your talk. Can you tell us a bit more about 6G? What's the difference between 4G, 5G, 6G?
It's a very good question. And it's a very complicated question because there's disagreement between people like Ericsson and Nokia and operators like AT&T or T-Mobile. I mean, what Ericsson says is, guys, it's time to spend more money. And the operators say, you know, we spent money on the last one, and you promised we were going to get all sorts of new services, and we didn't. Why should we spend more money now? Why do we have to have new technology? Why can't we just have software upgrades? So that's the discussion that's playing out at the moment. So I would say there isn't consensus about what it should be. There's also, I mean, there's a difference between wireless standards and internet standards. Somehow internet standards are a lot more productive, right? You can change them easier. You can adopt them easier. There's a lot more friction in wireless infrastructure standards. One is more closed, one is more open. Radio is perhaps less flexible. But yeah, it's a great question.
Thank you very much, Robert, for your excellent talk. You say it's related with group theory, most of it, right? But I saw statistics and also stochastic processes everywhere. I saw mixtures, distributions everywhere. Like, in a sense, and as a statistician, I haven't seen much of this theory, but I see a lot of relation, like the last examples you've shown, where you have a lot of mixture distributions, in a sense. So, in your take, which is the overlap of these areas that I'm sure you know very well? Like, in what sense is this somehow in an ideal place, or it would benefit from more interaction?
So I think that, look, communications is statistical. So in the larger sense, it's all about statistics. I think that electrical engineers tend to design very simple things like equalizers using MMSE techniques. Statisticians know that you can do all sorts of complicated things like variational Bayes, which are simpler. And I think that that's the overlap. I mean, the more you understand about the distribution, the less complex are going to be your receiver techniques.
I have a question mainly from the point of view of students, whether you could give them some advice on how to step successfully with one foot on mathematics and another one in engineering, so that they can successfully participate in that.
Let me actually tell you, let me go back to the very beginning, this Cohere. I'll tell you a Cohere Technologies story. So Cohere is a company that was founded by a mathematician called Ronnie Hadani, who was a professor at the University of Texas, Austin. And Ronnie is a really, I've known Ronnie now for almost 20 years. And the way that we got to know one another, our son was at the University of Chicago. And one day I got an email out of the blue which said, "I'm your son's TA. I'd like to talk to you about signal processing." And he had started to think about, so I mean, Ronnie is look, I'm sort of an applied mathematician. He started out as an incredibly abstract mathematician. He did representation theory. He was Drinfeld's postdoc at the University of Chicago. What I just described today, in its most abstract, is representation theory that Ronnie knows. Ronnie founded this company with someone called Shlomo Rakib, who's really an engineer. And I think it took Shlomo something like 5 years of asking Ronnie questions in order to make it something approaching a system. And so it really takes that kind of dialogue. I mean, Shlomo was convinced that Ronnie had the germ of something. And, you know, they talked until they understood each other.
More questions? ¿Más preguntas? Aunque las traduzcamos al inglés. Creo que hay una.
So you think that as an applied maths student, we should take more like classes or go deeper into the pure maths? Like when I started a career, I thought that my goal was to transport the problems from like engineering or social sciences to something more mathematician. But with this idea, I think like we should introduce the pure mathematics into the problems that we have in social sciences, in engineering or physics. Like we should go more with the pure maths in order to understand better.
So what I think is the following, that you have these domains like social sciences and humanities, and then you have applied mathematics. And for sure, applied mathematicians can say, can be useful to people in humanities and social sciences. But if that's the only thing that happens, you can't sustain it. I mean, I think that what's important is to have a dialogue between the two where value passes in both directions. So it should be that there are problems in social sciences and humanities that are new perspectives on applied mathematics, as well as the other way around. I think that you only discover those connections by talking about a problem and by so one of the things that I did at AT&T was I ran the networking center, and we had a seminar every 2 weeks. And the only rule for the seminar was that you could only talk about what you knew for 5 minutes. The other 25, you had to talk about something you wanted to do, but you didn't know how to. And some really interesting things came out of that. We had a really good statistician, Corinna Cortez, who now works for, she works for Google. She was doing signatures, so trying to describe typical behavior of telephone numbers in North America. But this was signatures at the scale of 500 million. And she was doing it by hand. And she got up and she said, here's what I'm doing. I just can't sustain this. I don't have enough hours in the day. And there were computer scientists in the audience that managed to make a domain-specific language for dealing with signatures at that kind of scale. The interesting thing about this story is they wrote a paper and they sent it to KDD, which is the flagship data science conference. And the first year they sent it, it got rejected because the program committee didn't think it was a real problem. Second year they submitted it, they got the best paper award. I mean, so I think it's only this dialogue between, first of all, I think that dialogue between different sorts of people is interesting. I mean, it's like, you know, how do applied mathematicians have social life? Maybe it's through dialogue like this, but that's what I think.
If there isn't any other questions, let's thank Robert for his generous talk again.